TagRuler, span-level data programming by demonstration. We propose a system that extends the data programming by demonstration framework to span-level annotation rules. Data programming by demonstration is a framework that allows users to build labeling functions without coding literacy. TagRuler extends this human-in-the-loop programming technique to span annotation problems by implementing novel features. This allows users to scale up their labeling capacity beyond what was possible before, saving time and resources. This is especially important because span labeling is one of the more time-consuming tasks, both for labeling and for data programming. We are especially interested in how TagRuler can help in the medical domain because it's a great example of a field where we can't expect domain experts to spend copious time labeling, yet model performance is obviously critical. This is a perfect scenario to leverage data programming, but until now, this required the domain expert to have programming expertise. So, let's see how we can leverage TagRuler on a chemical disease annotation problem. One advantage of TagRuler is that I don't need to annotate every instance of a chemical or disease in each example. I only have to choose a few examples that I think are representative. For example, here I annotated the second instance of chloroacetaldehyde as a chemical because I thought it provides more contextual information than the first instance. TagRuler suggests labeling functions based on my input that detect semantic and syntactic context. In this case, Elmo and BERT embeddings are used to detect semantic similarities. I'm going to select both of these rules so I can compare how they perform. And now I'll delete the Elmo labeling function for ifosfamide because it has lower precision than the BERT similarity rule. When the system samples the next text, it uses an active learning strategy to sample the sentence that can best improve the performance, saving me time. Let's see how the new rules are performing. I found adenocarcinoma BERT rule has a lower precision compared to others. I can click to see more details of each rule, including example annotations or mistakes. This helps me decide if I need to delete a rule or if I need to create new rules to counteract the types of mistakes that this rule is making. For example, this rule is tagging several chemical names, which I hope I can fix as I add more rules for the chemical class. I also see that it's falsely tagging numerical values. So for some mistakes I observe, building labeling functions for the other label class is crucial for higher precision and lower false positives. So I annotated numerics as the other class, and I select corresponding labeling functions. Throughout this process, I receive continuous feedback about my labeling performance. I can get a more accurate idea of the quality of my labels by training a conditional random field model, or CRF. At this stage, the model accuracy is low. Specifically, it looks like the precision for the chemical class is even lower. So let's investigate the lowest precision labeling functions. So looking at the example annotations here, this labeling function seems to mostly work well. I can add a rule labeling verbs as other in order to counteract some of these mistakes. After creating 42 labeling functions, I sorted rules by condition in order to make sure that I don't have rules that are too similar. This relies on the principle that ideally, my rules should have independent errors. I removed some similar rules, leaving only the higher precision versions. Now, let's try retraining the model. So, in just 30 minutes, I've created 39 labeling functions, which achieved an F1 score of 0.516 in my CRF model. I can export these labeling functions easily and apply them to any dataset I want. Please check out our GitHub repository for more information about the system and to try it out. Thanks for watching.